Good afternoon, students. Let us start today's AEC lab class. We had discussed clipper circuits and clamper circuits till now. The clamper unbiased circuits we had discussed in the last lab class. Just to make you recall whatever we had discussed about the clamper in the last lab class, I had told you about something called tau. Tau is time constant. So I'll write it here. Tau equals R into C. And T equals 1 by F. Just a minute, I have a call here now, official call.
Students, you can give your utterance. I'll call your name. Vignesh, user number 78. Hi, Vignesh. Is he there? No, he's not there. Yashwant. Lakshman. Nidhi.
Present, sir.
Nikhil.
Present, sir. Hello.
Nikita.
Yes, sir.
Nirmit. Nirmit. Nishant. Jashwant. Jashwanti. Rakesh. Pawan.
Yes, sir.
Rakesh is there. Pawan. Harsha Chakravarti. Ola. Kamalnath. Puneet.
Present, sir.
Puneet Yam.
Present, sir.
Harshit Gowda. Rukita. Rakesh.
Yes, sir.
Rakesh. Rakesh Kumar Patel. Rakshita Sharma.
Yes, sir.
Rohit.
Present, sir.
Sutish.
Yes, sir. Present, sir.
Govardhanan. Sachinar.
Sir.
Sagar.
Yes, sir.
Okay, let me continue the class now. In the last class, we were telling that time constant tau equals R into C. So this unit for tau is seconds only. Similarly, we had told about T. T is 1 by F, that is 1 over frequency. Now the condition for the clamper circuit to work is that T must be, or sorry, frequency must be much larger that way. If frequency is much larger, duration will be much lesser, so that we should not give the time for the capacitance to discharge. That is the idea. So the condition is that T must be much less than tau. Okay, or in other words, F must be much larger than tau. I cannot write that. I will not write that because F and tau are not relevant that way. Let me not write. So remember this. In the first 1 or 2 cycles, when capacitor passes the AC, now this diode is forward biased in the negative cycle. So naturally, when this diode is conducting in the negative cycle, there is a least resistant path, and this will become plus, this will become minus. So later on, the capacitance remains charged after some time, like this. Capacitor will work like a battery afterwards, which means we will not give the time for the capacitor to discharge through the R, because again one more negative cycle will come and it will charge the capacitor. That's why I was telling T must be much less than tau, or tau must be at least 10 times T. In that case, capacitor will never discharge, capacitor will hold that charge. Later on, capacitor will work like a battery. If this is 10 volts peak to peak now, capacitor will be charged to Vm, that is 5 volts. If it is 10 volts peak to peak, capacitor will charge to 1 peak, that is 5 volts. So that way you can see later on this works like a battery, and the battery will superimpose the power on the AC. As I told you in the last class, now AC and DC are in series. When AC and DC are in series, they will get added up. But when AC and DC are in parallel, they will not get added up. When AC and DC are in parallel, only DC voltage will be available there. That is because DC is stable, DC is strong. DC will never change its value. So that way the effect of AC will not be there when the voltage sources are in parallel. But in this case, the voltage sources are in series. AC and DC both are in series. So that way, plus 5 volts get superimposed on the AC signal. Similarly, the other negative clamper, we had seen the negative clamper in the last class also. Now this will work in the positive cycle. In the sense, in the positive cycle, the diode conducts. In the negative cycle, diode does not conduct. So in the positive cycle, there is least resistant path. So the capacitor will have plus side here, minus side here. And the capacitor will get charged to 5 volts. Again, 5 is the Vm. So when it charges to 5 volts, negative side is this side. So minus 5 volts get superimposed on AC. So you can see that minus 5 volts is coming here, due to which the signal goes down. So this was the capacitor and clamper's working principle. Now today, let us go to the last set of clamper circuits, which is biased positive clamper and biased negative clamper. So let us see this particular circuit here. Now look at this diode. Can anyone tell me, wait a minute, let me write an example here. Let us say this VB is 2 volts. Wait, let me use a different color. Let us say this VB is 2 volts. And let us say this is 10 volts peak to peak. This is now 10 volts peak to peak. Can any of you tell me when will this diode conduct? Can any of you tell me? Now 10 volts peak to peak. That means this is now 5. This peak is 5. And this peak is minus 5. This peak is minus 5. Now, can any of you tell me, when will this diode conduct? Will it conduct in the positive cycle or will it conduct in the negative cycle? No one is telling. Okay.
So positive cycle.
In the positive cycle, the diode will not conduct, because in the positive cycle, cathode is connected to plus, its anode is connected to minus. Already its anode is connected to minus. When anode is connected to minus, diode will never conduct. Now when cathode is connected to plus, it is totally reverse biased. It will never conduct. So in the positive cycle, the diode will never conduct. In the negative cycle, when will this diode conduct? Can anyone tell me? Tell me, Nikhil, you're not audible.
So -5 at the peak value.
-5. Not exactly. Okay, I'll tell you the answer. This diode is normally reverse biased. See, normally when the input signal is not there, then also diode is reverse biased, because the anode is connected to -2 volts. You can see the battery symbol here. This battery is negative. That means in the normal condition, when the input signal is absent, diode is reverse biased. Now in the positive cycle, when the signal increases, anode is already in the connected to the negative plate, but cathode is now connected to positive. So in the positive cycle, let us say in the positive cycle, when the signal is coming here, diode will remain reverse biased. And let us say in the negative cycle, until this voltage reaches -2, until the voltage of the signal reaches -2, diode will remain off. So diode will conduct in the negative cycle only when the negative cycle's voltage reaches beyond -2. Let me again clear the screen and let me annotate differently. Let me use a different color now. So now diode will not conduct here. Okay, I am shading it. And diode will not conduct here also. Let us say this is up to -2. Diode will not conduct. So beyond that, diode will conduct. That means the diode will conduct from this -2 till -5. You get this point? In the positive cycle, diode will never conduct. In the negative cycle also, until the voltage reaches -2, diode will not conduct, because this VB is -2 in our example. When this VB is -2, as long as this -2 effect, that is reverse biasing the diode, until it is overcome, the diode will never conduct. When this will be overcome, when this -2 is in the other cycle, in the negative cycle, when that voltage is coming from this direction. See, now in the negative cycle, current is flowing in this direction. In that direction, when this effect of battery is overcome by the effect of the AC signal, then the diode will conduct. That is, in the negative cycle, the diode will conduct in this unshaded portion from -2 till -5. That means 5 minus 2 is 3 volts. To an extent of 3 volts only, diode conducts. Okay. Now when diode conducts, that diode is the least resistant path. So there will be capacitance charge here. Now as you remember, tau has to be larger than T now. When capacitor charges, we will not allow it to discharge. That way we choose the RC values. Now after a few cycles, this diode will keep conducting always in this unshaded portion and capacitor gets charged. Now can anyone tell me what is the voltage across this capacitor? If I write this battery here, can anyone tell me what is the voltage across this capacitor? 2. No, it is not 2 volts. Any other answer?
Sir, 8 volts.
8 volts. No, wrong. 5 volts. No, wrong. It is not 2. It is not 2 volts. Remember, the diode conducts only when the effect of the battery is overcome by the AC signal. So when that effect is overcome, I have already told you the unshaded portion. Here in the screen, we have an unshaded portion. During that unshaded portion only, diode is conducting. That means diode is conducting between -2 to -5. All other conditions, diode is off. So what is the difference between -2 and -5? 3 volts. It is 3 volts. So this capacitor will remain charged in this direction only for 3 volts. Okay.
So what about then from -5 to -2 again?
Yeah, -2 to -5 diode is conducting, right?
Sir, and then again -2. The graph is going to.
Yeah, it is going to conduct. See the difference. The peak value is -5 here. So between -2 to -5, coming back to -2, the diode is conducting. But the diode is conducting here, capacitor will not discharge there, right? So capacitor will charge to this difference only, right? The difference is 3 volts. Once the capacitor is charged, it will never discharge, no? You got the answer?
Yes.
Okay. So you should always visualize that only when the diode is conducting, capacitor is charging. But capacitor will charge to the value, maximum value up to which diode is conducting. So it is reaching in the negative cycle, it is reaching -5. So between -2 to -5, diode is conducting, but capacitor will not discharge later on. Again, in the next cycle comes, capacitor will retain the charge. That means capacitor will retain the charge up to this peak. Because it is retaining the charge up to this peak, -5 and -2 difference is 3 volts. So capacitor is charging to 3 volts. Now what happens is, this 3 volts, positive side is towards the output. So plus 3 volts gets added to the input. Now you can see the signal goes up by plus 3 volts. So how much should I write here now at the top? How much should I write here at the bottom? Can anyone tell me how much should I write here at the top?
8.
Yeah. It was earlier 5 volts, now it is 8 volts. 5 plus 3, 8 volts. What about here now? Last below?
-2.
It is -2. Because it was -5 plus 3 volts is -2. So the signal gets shifted upwards by 3 volts. This way, now the signal has not remained pure DC. You can see the signal is in the first quadrant also, it is in the fourth quadrant also. Then the signal is not pure DC, it is now AC also, partly it is AC. That is the wonder of these clamper circuits. It is in the earlier two circuits, it had become completely DC. Now here it has not become DC, partly it has remained AC. But still the signal got shifted up by plus 3 volts. Now my question is, if at all we reverse this VB, what will happen? If at all we reverse this VB, what will happen?
Output will shift to the negative side.
Output?
Shift towards the negative side.
No. Think again. Rohit is thinking that if we reverse this battery, then automatically it will become a negative clamper. No, it will not become. See, remember this. positive clamper with the negative bias. If at all I reverse this, then it is becoming a positive bias. So does it remain a clamper? Think again.
So it becomes DC, sir.
Yeah. Who's told this?
So Nikhil.
Nikhil, very good. Now, if you reverse this battery, what happens is diode remains forward biased. Diode permanently remains forward biased. When diode permanently remains forward biased, always at the output there will be DC. Because this battery comes in parallel with the AC and diode is conducting. Diode is conducting, battery comes in parallel with the AC. So when DC and AC are in parallel, it is the DC that is powerful. I'll write it here. See, instead of this negative terminal, if this side, if it is positive terminal like this, and if it is 2 volts, then always the diode will be conducting, right? Always when the diode is conducting, ignoring the voltage drop across the diode, always this voltage DC will be across the output. That's all. So this will not become a clamper. That is why positive clamper is always with the negative bias. Now we want to have a negative clamper, automatically we should have positive bias. So our next circuit is negative clamper with positive bias. See, this is the circuit now. Now, again, let us say this is +5, this is -5, and let us say this is +2. You can see now, positive plate is connected to cathode, means diode is reverse biased. What happens now? In the positive cycle, what happens? Can anyone now tell me, when will this diode conduct? No answer? It is just the reverse of the previous circuit. In the previous circuit, the diode conducted in the negative cycle after the signal crossed -2. Here again, let me annotate. If at all this is 2 volts, now let us say this is +5, and let us say this is -5. Now, this diode is normally now, see, cathode is connected to positive, so it is reverse biased. So if this diode has to conduct, the anode must be larger than +2 volts. So what happens is, until this signal reaches +2 volts, diode will not conduct. Now when it reaches +2 till +5, diode conducts. In the negative cycle, negative is connected to anode, so the diode will never conduct. So I am shading this portion. Wherever I have shaded, there the diode will never conduct. Now this diode will conduct when the positive cycle goes above +2 volts. That means +2 to +5 is +3 volts. So now as the diode is conducting in this direction, this will become plus, this will become minus. So now after about 10 cycles or so, the capacitor will behave like a battery with 3 volts across it. Just like the previous example. Diode is going to conduct from +2 to +5, and then when it is conducting, capacitor will remain charged. Capacitor will never discharge because we have that tau greater than T, much greater than T. So because of that condition, now you can see the capacitor remains charged at 3 volts, and what happens is now, because of the negative terminal at the output side, -3 volts is superimposed on AC. Now this DC and AC are in series. So always when AC is coming to the output side, that 3 volts has to be subtracted from the AC, that way from the instantaneous value. So naturally you can see that the signal goes down. If the signal goes down, can you now tell me how should I mark these two values?
2 and
Can you tell me? Yeah.
2 and -6.
It is +5 minus 3 is here, it is now 2. Okay, and here it is -5 minus 3 is totally -8. Okay, between +2 to -8, you can again see it is totally 10 volts peak to peak only. Now the signal is shifted down to the fourth quadrant to an extent of 3 volts. You can see this is a negative clamper with the positive bias. You see this? If at all we have to have a positive clamper, we should have a negative bias. If at all we want to have a negative clamper, we should have a positive bias. Okay, we cannot have a negative clamper with the negative bias. Again, why? If at all we reverse this battery side now, negative gets connected to cathode and the diode is always on. When the diode is always on, across the output you will always get -2 volts. So it will not work like a clamper, as DC comes in parallel with AC. So these were the discussions of the biased clamper circuits. Next, I will proceed to the next experiment. Before that, if you have any questions, you can ask me regarding the clampers. Otherwise, I will proceed to the next experiment. Any questions, students? Okay. No questions means let me proceed to the next experiment. Yes, this is that particular experiment. RC coupled amplifier. Already in the theory course, you have studied BJT amplifiers. Now we call it as a single stage BJT amplifier. Single stage means only one transistor we use. We call it as RC coupled because for biasing we have resistors and then we have capacitors for coupling. Now let me show you the transistor. We are going to use a transistor called SL100. The name of the transistor is SL100, that is a manufacturer's type number. Now this is a metal can transistor. You can see the picture here. This transistor is a discrete transistor, means you can handle it as a single transistor. It is not an integrated transistor. Integrated transistor will be much smaller in size. We are going to use a discrete transistor in the labs. So now this is a metal can. Metal can in the sense the transistor is covered with the metallic body, and in general collector will be the body for any metal package transistors, because collector is the largest region and at the collector there is a collector current flowing. So normally when they manufacture transistors, the region collector is always largest out of all the three. Now what they do is, when the transistor gets heated up, as collector is larger, they connect the collector to the body itself, so that if it is a metal package, heat can be easily dissipated into atmosphere. You know that in case of an amplifier, transistor works in the middle of the load line. That means the transistor is neither on nor off. So if the transistor is completely on, across the switch, ideally there is no voltage at all, because switch is completely on. Now if the transistor is completely off, then the total voltage is across the switch, but there is no current flowing. You know that P equals V into I, right? When P equals V into I, when the transistor is completely on, across the switch, voltage is almost zero. Even though current is flowing, voltage is zero. So we can say that the power consumption is zero. Similarly, when the transistor is completely off, at that time also we can say current is zero now, because switch is off. Just visualize your own switches at home. If the switch is completely on, then across the switch there is no voltage. All the voltage is going to the load. The load can be a tube light, load can be an electric bulb, load can be a fan, load can be a television, fridge, oven, washing machine, whatever. Now when you have electrical switches at home, if the switch is on, there is no voltage drop across the switch, because voltage across the switch is zero, power consumption of the switch is zero. Similarly, when the switch is off, what happens is current is zero across the switch. So even the voltage is there across the switch, there is no current. So power consumption when the switch is off is also zero, ideally. Now let us say when you have a fan regulator and you have kept the fan in the speed 3. Now what will happen? In the fan regulator, when you kept the speed as 3, now only part of the voltage is going to the fan. All the 220 volts is not going to the fan. So fan will be revolving, rotating in the revolution or rotating in the medium speed. Now, there is no full voltage coming to the fan. So power consumption across the fan will be half now. If the fan was running in full speed, then we should say there is a maximum power consumption at the fan. Now, when you keep the fan in half speed, fan is taking only 110 volts. Imagine that way. If it is 110 volts into that particular current, so half of power is across the fan. Remaining half power will be where? It will be across the regulator itself. Okay. That is the point I am trying to make here. The point is, in an amplifier, we are using the switch in half on, half off condition. So here, neither the voltage is zero, nor the current is zero. Switch is half on, half off. And when neither the voltage is zero, nor the current is zero, there is a voltage across the transistor that is VCC by 2, and there is a current across the transistor that is IC sat by 2. You are already familiar with these terminologies because you have studied this already in the theory course. So if the VCC by 2 into IC sat by 2 is the power across the transistor now. So the point I am trying to tell you is, in the active region, transistor consumes power. In the saturation region, it does not consume power because voltage is zero across it. In the cutoff region, it will not consume power because current is zero across it. But in the active region, neither the voltage is zero nor the current is zero. Voltage is half of VCC. Current is half of maximum current. So there is going to be power consumption. When there is going to be power consumption, always power gets dissipated as heat. Always energy gets transformed from one form to another always. So here, when we work with electronic devices, the power gets converted into heat, and because of that heat, the life of the transistor itself may get reduced. Now to prevent that, they make the transistor's body as metal. That is the point here. Otherwise you may ask, why the transistor must be of metal package? The reason is this. When you come back to college, you can see all these transistors physically, or when you work in the lab, you can also observe the power supplies. Below the power supplies, you will see some very big transistors, and they are all connected to another metallic structure called heat sink. There will be aluminum fins connected to that heat sink, and along with the heat sink, the transistor is mounted. The reason is, even though the transistor is of metallic body, all the heat that is there across the transistor may not be effectively dissipated, and if the temperature of the transistor increases, life of the transistor gets reduced. Now to compensate that, the transistors are mounted on an aluminum heat sink so that the aluminum will dissipate the heat. Just like when someone is having a heavy fever, what they do is, on top of the head, they connect one wet cloth. When they put one wet cloth on the forehead, the heat that is at the head will get absorbed by the wet cloth. In the same manner, this transistor, when we work it as an amplifier or in the power supply, it will always be having this fever. all the transistors are going to have this fever because they are always going to consume power and they are going to heat up. If we have to increase their life, then we should mount them on metallic cases so that heat will be absorbed or dissipated. Now, I told you that the collector will be always with the body. When the collector is the body, you can see this 1, 2, 3. Always you can see in this transistor, whichever pin is connected to the body, you can easily identify. The pin will be connected to the body, that is collector. And then you have, in the middle, you have base. The other one is emitter. Emitter and base, sorry, 1 and 2 are emitter and base. Emitter and base are insulated from the body. That also you can see when you physically see this transistor. Now there is this small key here. In many metallic cases, they put this small key. This key indicates that nearer to the key, whichever is the terminal, that is emitter. You remember this? Nearer to this particular key, whichever is the terminal, that is emitter. Then middle one is base, last one is collector. This is how you have to identify the 3 pins. If you reverse these pins, what will happen? In BJT, emitter and collector are not interchangeable. Collector is larger, emitter is smaller. Emitter is heavily doped, collector is medium doped. So we cannot reverse emitter and collector. If we reverse emitter and collector, it will not come into active region. It will not come into active region because instead of the base to emitter junction, now you have a base to collector junction below. And instead of the base to collector junction at the top, you will have a base to emitter junction above. And it will have a reverse effect on the switching of the transistor and it will not turn on properly. But transistor will not fail. You don't have to worry. Transistor will fail only if the rated current is exceeded. Now here the transistor will not switch on properly itself if you reverse emitter and collector. So otherwise nothing will happen. But you should be careful. You should identify these pins exactly. Then only you should connect it to the circuit diagram. Now let me come to the circuit diagram. This is the transistor where you are going to connect. And you will have 4 resistors now. When you come to the lab, you will be given these 4 resistors. You will have to identify these 4 resistors values. You have already studied this color code in the physics lab, right? Black, brown, red, orange, yellow, green, blue, violet, gray, white. This already you know. B, B, R, O, Y, G, B, V, G, W. That is how I remember it. How I remember it is, you may have many different observations like Baby Roy, Great Britain, all those things you may have. How I remember is, first is black, last is white. That way visualize. Then between this black and white, in the middle, there is this rainbow color. Red, orange, yellow, green, blue, violet. Indigo we will not have. Out of the rainbow color, we will have only 6 colors. Because indigo and blue are almost the same that way. They don't use indigo here. So B, B, R, O, Y, G, B, V, G, W. That is how I remember. So now black, then brown, then red, orange, yellow, green, blue, violet. After violet, it is gray. After gray, it is white. This is how I remember the color code. So using the color code, you will have to identify the values of the resistors. Okay. Now using those resistors, you will have to connect this circuitry. Now, there is a design here. Now we will have to design this particular circuit for VCC 10 volts. See, given VCC 10 volts, VCE has to be normally 5 volts, right? VCEQ has to be VCC by 2. So naturally, VCE is 5 volts. Now let us consider the ICQ as 2 milliampere. ICQ as 2 milliampere. This beta is 100. Actually, that beta is missing here. It has to be written as beta equals 100. Okay. So now assume VB for 0.7 volt for silicon diodes. Let us have V equals 10% of VCC. These are all design values. As I told you in the theory class, when you have 2 resistors here, when we have to decide upon the VCE, now this is plus 10. We know that across collector and emitter there must be plus 5. but there are two unknown parameters here. RC and RE both are unknown. Now we should have a design criteria where we will consider VE to be 10% of VCC. So VE we will choose it as 1 volt. So now when we choose VE as 1 volt, we can easily find out RE is VE by IE. That is 1 volt divided by 2 milliampere. IE is 2 milliampere, right? Because we have chosen collector current to be 2 milliampere, quiescent collector current to be 2 milliampere. So now RE is VE by IE 2 milliampere. 500 ohms is the value. Now 500 ohms is not the standard value. As I told you in the theory class, I had showed you in the chart also in the module 1. We have something called E24 series, E48 series. So 500 ohms is not a standard value. We can go for the nearest value, that is 470 ohms. So you will have those respective colors, BBROY. So you will have yellow color for 4. Then GBVGW, violet you will have for 7. Then you will have brown. Brown indicates the last color is multiplied by 10 power 1, that is 10. So you will have to identify such resistor with such color, that is 470 ohms. Now we apply KVL to the output. RC equals VCC minus VC minus VE divided by IC. This you are already familiar in the theory class. So we get RC equals 2 kilo ohms. We can use 2 kilo ohms. Near standard value is 2.2 kilo ohms. We can use 2.2 kilo ohms also. We can use 2 kilo ohms also. Now, going for the approximate analysis, this you remember, right? Beta RE must be greater than or equal to 10 R2. Using that particular condition, we should choose R2 as beta into RE divided by 10. So we will choose R2 to be around 5 kilo ohms. Nearest standard value is 4.7 kilo ohms. Now, ignoring the IB, we can find out VBB or V2, that is VE plus VBE, 1 plus 0.7, 1.7 volts. So now we can find out R2. Now we have this VBB or V2 is 1.7 volts. Using that, we can find out V1, that is VCC minus V2, 10 minus 1.7 is 8.3 volts. Using this, we can find out R1. R1 is V1 by V2 into R2. Based on the voltage divider rule, we get around 22.9 kilo ohms. We can use the nearest value is 22 kilo ohms. This way we got R1, R2, R1, R2, RC, RE. All the 4 resistor values we have got now for the given Q point. Now that is the design here. Okay, this is that particular diagram and we will have the design here. Now we can choose C1 and C2 based on our range of frequencies. Normally we choose C1 and C2 to be around 0.1 microfarad, sometimes 1 microfarad, sometimes 10 microfarad, depending upon the application. Now in the lab we will choose 0.1 microfarad for C1 and C2, and for CE we will choose 10 microfarad or 100 microfarad. The reason is, can anybody tell me? Why should I have the bypass capacitor much larger when compared to the C1 and C2? I have told in the theory class already. Anyone remembers? There are 19 students in the class and nobody remembers. Very good. The reason is, yeah, tell me. Anybody is trying to tell something? Okay, let me proceed. The reason is, we want this VE to be very stable. When we want this VE to be very stable, the Q point should not be affected, even if the part of the AC signal comes here, because this is a base to emitter diode. Part of the AC signal will come to the emitter as well. Now that should not happen, means all the AC should be going to ground. We want AC only at the collector because of the switching action of the transistor. Otherwise, across RE, it should be pure DC. If we want it to be pure DC, then naturally the value of C must be much larger. because we want this capacitor to work like a DC battery there. So the value of C will be 10 microfarad to 100 microfarad, much larger, whereas C1 and C2 will be around 0.1 microfarad. Later on, we can connect on load resistance. I'll tell you the reason for load resistance later on. So this is the circuit which you are going to rig up in the lab. And we have something called signal generator, and we have something called cathode ray oscilloscope, and we have power supply for giving this VCC. Now you will connect this VCC and ground to the power supply. You will set your power supply to 10 volts. Then you will apply the input AC signal from the signal generator, and you will observe the output in the oscilloscope. But let us say in the lab, you rig up all these 4 resistors, 1 transistor, 3 capacitors, excluding the RL. We shall tackle the RL later on. Now, without giving the input signal, can you check whether the transistor is working in the active region or not? Can you?
Yes, sir.
Yeah, tell me how?
By using the multimeter, I'm finding the resistance, total resistance.
Which resistance?
The total.
No. We have this 2.2 kilo ohms here. We have 470 ohms here. Those are biasing resistors. How do we check that the transistor is exactly in the Q point? Multimeter is fine, but using multimeter or using oscilloscope also it is possible. But what to check and where to check? Any answer from anybody? Okay, the answer is you have designed the circuit for a VCEQ of 5 volts, right? Between collector to emitter, you want it to be 5 volts. That is how you designed the circuit. You want the transistor to be half on. Now connect the multimeter across collector and emitter and measure the voltage. You should get around 5 volts. Or else connect the multimeter between ground and collector. How much you should get? 6 volts. Because across RE it is 1 volt, collector to emitter it is 5 volts. Totally you should get from the ground to the collector 6 volts. That is one option. Another option is put the oscilloscope in the DC mode. When you put oscilloscope in the DC mode, connect the probe of the oscilloscope negative to ground, positive to this particular point, collector's point only. Where in the DC mode, you can check in the oscilloscope whether the collector is at 6 volts. If the collector is 6 volts, then you can check again at the emitter, this should be at 1 volts. So naturally 6 minus 1 is 5 volts. Approximately, you should get that particular value. Then that ensures that the transistor is half on. Now, if that is not happening, then what should you do? Let us say, when you connect the multimeter here and the collector with respect to ground, if you don't get 6 volts, let us say you get 10 volts only. What does it mean? Transistor is on or off? If you get 10 volts at the collector, then it simply means that whatever is the voltage here is appearing here, there is no current flowing here. When there is no current flowing here, it means that the transistor is completely off. Transistor is completely off means you have to check the connections at the base. Whether your R1 is properly connected to the base, R2 is properly connected, whether ground is connected, supply connected, you'll have to check all these connections again. Because transistor is not on. So you will have to verify all these connections thoroughly, only then you have to switch on the power supply And after switching on the power supply, you should verify that the collector is at plus 6 volts. Only after that, you connect the signal generator and switch it on and give the AC signal here. Otherwise, if at all you connect all these things at once in the lab, and if at all you find that some circuit is not functioning properly, you will not know what is wrong where. So it is better that before giving the input signal itself to the circuit, you will have to check whether the transistor is working in the quiescent conditions or not. Once you ensure that, later on you connect the signal generator, later connect the CRO here. Anyhow, RL we are going to discuss later on. Okay, now what you have to do? Now what you have to immediately do is right from 0 till let us say around 100 megahertz. Let us say you will keep this input value at around 10 millivolts as an example. Anyhow, when you come to the lab, we will tell you the exact voltage. Otherwise, let us say you are giving a signal of 10 millivolts peak to peak. When you give the input signal 10 millivolts peak to peak, and starting from 0 till let us say around 1 gigahertz. Okay, 1 gigahertz. Okay, right from 0, you give the signal 10 millivolts, frequency 0, 1, 2, 3 like that. Actually, you will not give it as 0, 1, 2, 3, 100, 200, 300, 400, 500, up to 1 kilo, then 2 kilo, 3 kilo, 4 kilo, 5 kilo, up to 10 kilo, then around 20 kilohertz, 30 kilohertz, 40 kilohertz, like that goes on till 100 kilohertz, 200 kilohertz, 300 kilohertz, like that go on up to 1 megahertz, 10 mega, 20 mega, 30 mega, like that up to 100 megahertz, again 200 mega, 300 mega, 400 mega, like that up to 1 gigahertz. I have already told you the usage of semilog sheet in the theory class, right? In module 3, we have discussed Bode plot, and I have already discussed about the semilog graph sheet. Now we are going to use the semilog graph sheet only in the lab class. That is why from 100, 200, 300 up to 1 kilo, 1000, from 2000, 3000 up to 10,000. That way you are going to keep on increasing the frequency, keeping the input voltage constant. You should never touch this. Once you set the input voltage to 10 millivolts, you should never touch this. Later on, keep on increasing the frequency. For each frequency, measure the output in the CRO. You will have to measure the V0. You will have to see the output waveform in the CRO, and you will have to measure the peak-to-peak value of the output. Later on, you will have a tabular column where you will measure gain, V0 by VI. VI is fixed to 10 millivolts. V0 by VI is the voltage gain. You will convert it into dB by 20 log V0 by VI. Now you have this frequency, 0 till 1 gigahertz. And you will take a semilog graph sheet. In the semilog graph sheet, x-axis is frequency, y-axis is gain. And you will plot the frequency response of this RC coupled amplifier. That is the first part of this experiment. Any questions here? Any questions? Okay, if there are no questions, let me proceed a little more. I have told you the procedure. Say, this is the observation table. VI, here they have given 30 millivolts peak to peak. You can keep it at 10 millivolts also. That when you come to the lab, we will tell you exactly what is the amplitude. Frequency in hertz, V0 in volts, AV equals V0 by VI, gain in dB. So this tabular column you are going to fill. After this tabular column, you will have this particular graph which you only are going to plot. X-axis is frequency, which is a semilog graph sheet, and y-axis is gain. Now you will get a plot like this only. In the theory class, I had already explained this. So in this graph, you will mark a point where it is 0.707 of maximum gain, or you will come down to minus 3 dB. minus 3 is basically 0.707's log only. You can actually find out the log of 0.707, you will get minus 3 only. So from the maximum gain, come down to 3 dB down, and wherever you identify these 2 points, extend them down, you will have one FL and FH, high frequency and low frequency. FH minus FL is the bandwidth of our RC coupled amplifier. Now this is the first part of the experiment, and I will stop here. The second part is measurement of input impedance and output impedance, that I'll discuss in the next class, because it's already 3 o'clock now. Now Prithviraj sir is going to give you a video link, and you can watch that video link, and I will conclude my class now.
Sir, I will send the utterance link, sir, in the chat box.
Okay, fine. So shall we end this meeting now, or will you share the video link here only, or?
No, I'm going to send the utterance links in chat box. Let them enter the utterance.
Okay, fine. So we will be ending the class now. Okay, students, if there are no questions, I will be ending this class now. This recording, I am going to put it in the Google class.
Sir, I want to put it in the chat box of the WebEx, so that only the participants who are there, they will enter the utterance.
Yeah, that is also fine.
Yeah, utterance is link is sent in the chat box. Students, you can enter the utterance. Yes, sir, it's posted, sir.
Okay. Okay, students, click on this link. I will be ending this meeting in a few minutes now. Fine. I'll be ending the meeting now. I hope all of you have clicked on the link. If anyone is still pending, please let me know immediately, or else I will be ending the meeting. Okay.
Sir, I guess they would have entered, sir.
Okay, okay. Okay, I'll be ending the meeting now.